Let's start our discussion on data mining. So last class we discussed why we need data mining, and we'll talk about that a little bit today, and then we'll go into a more different topics. So these slides are from the book. So the initial part of the course I will follow the book, and then the advanced topics are not in the book. So we will have to read the research paper. So let's follow the book for now. So why mine data? There are many different explanations for data mining. But as we have discussed last class, that data mining is important because our main goal is info retrieval. And info retrieval algorithms will work much better if we have data mining. So better why? Two aspects. First aspect is that if we have raw data, nowadays we have a lot of sensors. We have tens of sensors on our body. Right? We carry tens of sensors. The smartphone itself has 5 sensors, more than 5. So we have so many sensors and we have a lot of raw data. So the dimensionality is increasing. The dimensionality of data is increasing. The info retrieval algorithms are very complex. And if the data dimension increases, then it becomes even more complex for us to run into info retrieval algorithms. So we have to, instead of running info retrieval algorithms on raw data, we need to run info retrieval algorithms on patterns. So extracting patterns from raw data is the task of data mining. That's what data mining does. That is one aspect. The other aspect is the curse of dimensionality. This problem is not very non-intuitive, but it's kind of non-intuitive, because you think that if I have more data, then I have more information, and so I can do better if I have more data. But turns out that no. So if you have more data, then the automated retrieval algorithms, they suffer. Why do they suffer? Let's let's discuss with a very small example, very simple example. You can't see anything. Right? Oh. Oh, that's right. Okay. Let's see with a very simple example. Nobody can hear, right? Yeah, so let's consider this, that there is a box. This is the set of all data points that we are interested in. Right? And let's say there is a circle. Right? There is a circle, and we are only interested in data points that are inside this circle. So these are data points that we want to focus on. Right? So an info retrieval algorithm, if we run an info retrieval algorithm, it has to ignore all this data, the white part, and it has to extract the data that is inside that circle. Right? So now, let's consider just one dimension. Let's say we have only one dimension. People in the back bench can hear me? Okay. So let's consider just one dimension. So one dimension, if we consider, we have to take projection of all the data points on this or this, whatever axis. Right? So let's choose this axis. So we take the projection. Right? We take the projection. Let's say this is a 5 cross 3. Right? So this x, the length of x is 4. Let's say 4, and the height is 3. Right? And let's say this radius is unity, 1. The radius of that circle is unity. So if that is the case, then what will happen? What is this length? 2, right? 2 units. So how much uninteresting data should the info retrieval algorithm purge if we have just one dimension? So you have 4 units of data, and the interesting data is 2 units. So the info retrieval has to purge out, like delete 2 units of data, right? Which 2 units of data is uninteresting. Now you increase the dimension. If you increase the dimension, you are considering both the dimensions, right? So now how much? So now we have 12 units minus pi r squared, right? So pi is what? 2.3. Oh, 3.14, sorry. 3.14. To me, all the answers are 42. Right? So 3.14. So how much? How many units? 8.86 units. So just by increasing one dimension, what is the factor of increase of the uninteresting data points? 4 times. 4 times it increases. So what does it imply? It implies that not only you take more time, yes, you take more time, but you have to go over a lot of uninteresting data to find out interesting data points. The more uninteresting data you have, less is your accuracy. So not only your time, the time taken for info retrieval, not only increases, but it might get less and less accurate if you have more and more data. Very counterintuitive. You would think if you have more supporting data, your accuracy will increase, but no. So that is the problem with dimensionality. And since we have so many sensors these days, so many sensors at high frequency, right? So too much data. We have too much data, and we suffer from this problem. So we need data mining. Data mining would remove these data, the uninteresting data, as much as it can. Right? So it will generate patterns. Maybe patterns are like this, that it will group, maybe clusters. It will form clusters. It will form clusters like this. This is one cluster. This is another cluster. This is another cluster. Another cluster, and so on. It will say that these are uninteresting clusters. So info retrieval will just not see these. And it will say that these three are interesting. So info retrieval now will focus on these three and will then expunge these data points which are not interesting. Right? So that becomes much easier task. So that is the main motivation of data mining. Then the other things are auxiliary. They will come. There's a lot of other motivating factors discussed in the book. So they are saying that okay, web data, e-commerce, credit card transactions, everything is generating data, and all these applications are generating data. You might want to correlate the data, right? From the bank transactions, credit card transactions, you might figure out what advertisement, what type of advertisement should I give in your Facebook feed. Do you like to eat? Do you like to ride, bike, right? So using one type of data or arguing about a totally different thing. That is also purpose of data mining. Recommendation systems. So you collect data from multiple users, multiple different users, and then you see patterns. Which user is similar to what user, what other user. So those are all data mining tasks. And that is what is the need for data mining. So there are other examples. I won't go over those because those we have kind of discussed. This medical viewpoint we have discussed last class. So let's not go over those. So let's go over the definition. So let's start from here. So if you see the book, there are many different definitions of data mining. There's no single definition, but what you can say is what is not data mining. That you can definitely say. But what is data mining? Saying that is a bit difficult. So what we can say is that data mining is just the method just before info retrieval. So there are many tasks. You have to first take data. You have to then select what type of data you want to use. There is pre-processing of data, so that involves digital signal processing, right? Filtering, taking average, mean, and all that. And then there are some transformations you might want to do. Right? In case of images, you multiply or product with the filters, different filters, and then comes data mining on the transformed data. And so make the transformed data, and then comes data mining. So data mining has several tasks. We will see what are the tasks later. And then after that you interpret, so which means you go to knowledge retrieval. So what is not data mining? The book says that okay, you cannot just say that just simple web queries are data mining. That is not data mining. Web query or search is not data mining. That is that can be helped by data mining. Right? So Google search is helped by data mining, but Google search as such is not data mining. It's just simple web search. Right? But it can be helped by data mining. So Google does a lot of data mining research. Amazon does a lot of data mining research. All these top companies. So we will talk about certain useful terms. This will set the tone for our technical part of the course. So you have to know about data. So data is typically represented in the form of matrix. Right? So one row of a matrix is one data point. So multiple rows means multiple data points. Now data is comprised of attributes. So for every data point there are different attributes. Attributes means each attribute is one dimension. So however many attributes, if you increase the number of attributes, that means you are increasing the dimensionality of the data. Attributes have attribute values. So if you want to have data means you have a matrix. Each row is one data point, and each column is a value of a specific attribute. Right? So let's clearly understand these terms. Right? So attributes are also called features. You can also call them features. So this feature, you have to do some feature extraction mechanism. You have to run some algorithms, and those are called feature extraction algorithms. So you extract those features, put it in the matrix, you get a data. Then you can have another type of attributes, which is called labels. Labels is a very specific type of attribute, and these labels are used later, we'll see, in classification. When we discuss classification, we'll see that labels are used in classification. Right? So feature vector dimension has the dimensionality D. Yes. So data mining uses many different concepts. As we have already seen in the topics last class we have discussed, it involves machine learning, it involves AI, it involves databases, association rule mining, that is a database concept. So it is a combination of these three, and machine learning, AI, as well as databases. But in this course, we will mainly focus on machine learning, which is pattern recognition. We will focus on databases, different types of data and databases. We will briefly focus on AI. Last semester, we didn't get a chance to focus on any AI. So we will now, in this class, we will focus on AI, which is mostly the reinforcement learning that we'll talk about, and the DeepMind, Google's DeepMind. And we'll talk about those AI concepts. So there are two types of data mining tasks. One is the predictive method, and the other is descriptive method. So predictive method means what? You predict the future. You're given some data points and you argue about the future. You don't argue about that data. You argue about future data. And what is descriptive? Descriptive means you argue about that particular data. You don't have any information about the future. So these two types. So use some variables to predict unknown or future values, and description methods is use human interpretable patterns that describe the data. So can you give me an example of prediction methods and some example of description models or methods? We will discuss this right in the next slide, but still, what do you understand by these two? Can you give some examples? Yes?
Extrapolation.
Extrapolation is what?
Of data, like we have like in Fourier transform we have extrapolation.
Fourier transform we don't have extrapolation. Fourier transform is just the data itself. So that is an example of descriptive.
Climate, weather trends,
Method, I am saying method, not application. Method. Regression. So regression is what? It's a predictive method. So which means that given the past data, you develop a model and then you use that model to predict the future. And that is the predictive method. What is the descriptive method? No. Classification is not descriptive. Classification. In classification, you train and then you test. When you test, you don't have the class level for the test data. You predict the class level for the test data. Right? The classification is not descriptive, it is predictive. Clustering is descriptive because you are arguing about that data. You are not arguing about any test data. Whatever data is given to you, you are arguing about that. So that is descriptive. So these are the different tasks. So as I said, in the next slide we'll see. So classification is predictive, clustering, descriptive. There is something called association rule discovery. We will discuss this in this class. That is descriptive. This regression, as we said, is predictive, and then anomaly detection. Anomaly detection is also predictive. So we'll talk about these in detail in this course. So let's first take into classification. So classification is the predictive method. So what do we do? There is something called the training data. There is something called the test data. Training data is collected to initialize the model. What kind of classification model can you imagine? Can you give me some examples of classification models? Logistic regression. What else? What? Naive-Bayes. Right? Many different methods are there. Neural networks. What? SVM. Yes. So what do you do in classification? So you have a training phase and you have a testing phase, right? So training phase, in there what you do is you have some training data set and you have to define a distance metric. Distance metric means what? How can you distinguish between two data points in the training data set? How will you distinguish? You cannot just say that it's different, but you have to say, quantify. How can you quantify? So you have to have some metric, distance metric. What are the distance metric? We will talk about that in the second chapter, I believe. Then you find the closest data points, right, in the training set. In the training set, what data points are closest? And then you classify. So classify means you configure a machine. What is a machine? Machine is just a set of equations. It's just a set of equations configured in a certain way. Right? So then you configure a machine. What do you mean by configuring a machine? Whenever you have equations, you have variables, you have coefficients. So configuring a machine means find out the coefficients. And what are those coefficients? Who governs those coefficients? Your notion of closeness. Right? Whenever you have a distance metric and you say that, okay, I have found the closest data points, those close data points will govern what are the coefficients of that machine. So that means you configure a machine. Now once you configure a machine, you have a next step, which is the test data. Right? You give a test data. And the test data, you give it to the machine and it predicts something about the test data, typically the class level. Right? So that is your classification. So there are many different types of classification techniques, right? Or not really classification techniques. Classification falls under different types of machine learning techniques. So classification is an example of a machine learning technique. There are other techniques. So this is a categorization of the different techniques of machine learning problems. Right? So if you say we can have two different types, supervised learning, unsupervised learning, and we can have these supervised learning, unsupervised learning are based on presence or absence of the labels of training data. Right? In a training data, if we have labels, then it is called supervised learning. If we do not know the labels of the training data, then that means it's unsupervised learning. And then there is the other dimension, whether the class levels are continuous or discrete. If the class levels are discrete, then we have classification or clustering. If the class levels are continuous, we have regression or dimensionality reduction methods. Right? So if we look at classification, classification is a supervised learning problem. Right? It's a supervised learning problem and it is a discrete problem. Why? Because you have definite, countably infinite number of classes. It is infinite, but countably infinite. Right? So you have countably infinite number of classes. That's why it is discrete. Now we will talk about clustering. Clustering is unsupervised. Why? Because the training data, you don't know the labels of the training data. You don't know the labels. But still you divide into countably infinite number of classes. It is not uncountable classes. Countably infinite number of classes you divide. So that's why the clustering is discrete. Then we have regression, as somebody said. So regression is again supervised learning, because when you do a regression, you know that this data belongs to a particular event. Right? So you build a model of a particular event, of the history. So that's why it is supervised learning. And it is continuous because you have infinite number of classes. Every data point is a class. Right? So that becomes, that's why regression is continuous supervised learning. Then dimensionality reduction, we will talk about dimensionality reduction. How many of you have heard about principal component analysis, PCA? And a lot of you, not the majority. Yeah. So PCA is a dimensionality reduction technique. What is it? So you are given a data set, you figure out which ones are the important dimensions. And represent the entire data set using only those important dimensions. The other dimensions you can ignore. Okay? Either ignore or you can represent as linear combination of the important ones. That is PCA. So we'll talk about that also. So these are the 4 different techniques we'll talk about. Apart from regression, we'll talk about those 3: classification, clustering, and dimension reduction. Regression, we'll see if we have time, we can discuss. So let's go back to classification. So classification means you are given a collection of records, which is called the training set, and each record contains a set of attributes. So we know that the attributes are on the columns, right? And each attributes have certain values. These attributes can also be said, can also be called features. So attributes have attribute values. Attribute values means these are raw numbers, real numbers, or imaginary numbers or integers, but these are numbers. So the goal, so you have to find a model for class attribute as a function of the values of other attributes. So this, among all the attributes, you have one attribute which is called class labels. Class labels is also one attribute. So the aim is, can you express the class level as a function of other attributes? That is the aim of classification. Okay? So what is the goal? You are given a previously unseen data, and you have to figure out what is the class level for that particular data. So that's why it is predictive, because you are given an unseen data. So classification is a predictive and algorithm or predictive data mining method, and the unseen record is called test data. Test set is the collection of test data. So this is an example. So you have a database. There are 4 attributes and there are 10 data points. 4 attributes, 10 data points. Now this is your training data set, and the class cheat, that is the class label. Now this is a training data set, so you learn a classifier. What classifier you learn, we'll come to that later. Just learn some classifier. Right? So classifier means it's some model which expresses the attribute cheat as a function of refund, marital test status, and taxable income. Right? Then you are given a test set. And in the test set, you have values for refund, marital status, taxable income, but you don't have values for cheat. You have to figure out the values for cheat. That is the classification problem. There are many example applications. Well, we can go through, let's go through one of them. Images, object recognition is very hot topic. Object recognition. So what you do is you take images of objects and you label them. So that's a football, that's a cat, house, table, and so on. You label them, and then you get some other object, some other image, and you would want to figure out the object. Right? So you learn a machine. Typically, you learn a convolutional neural network (CNN), right? And then you give a test data, and CNN says, "Okay, this is apple." You give an apple, image of an object apple, then it gives you an apple. Right? Face recognition and all that. That is an example. Our 5th assignment will be an example of classification. So we have gestures and we figure out what gestures are those. And that is what we will have our 5th assignment. Most probably we will have to use deep neural networks for that. We will discuss that later. So those are examples. So basically what is happening, that you are figuring out a function f, right? And given an image, the f outputs the class levels. So you give an image of an apple, it says apple, tomato, it says tomato, cow, it says cow. It can also say, if you give an image of cow, it can say apple. And it is possible. So this is the framework, classification framework. You have to figure out a function f. So y is the output, f is the prediction function, and x is the image feature. So you have to give some features, attributes as inputs. So what you do is, in the training, you given a training set, and So training set is a set of labeled examples. So all the labels you know. So once you know the labels, you develop a prediction function f by minimizing something. And you minimize something. What thing do you minimize? The most intuitive thing to minimize is the prediction error on the training data set. Right? So you assume that, let's say I don't know the class. Right? Let's assume that I don't know the class. If I don't know the class, what is my accuracy now? Right? So that is the prediction error. So you take prediction and you want to minimize the prediction error on the training data set. And then you are given a test data, you classify that. Now there is a fundamental question here. Is it very good, or is it a good practice to minimize the prediction error on the training set as much as possible? Why not? Overfitting, right? So we'll talk about a concept called generalization error a little bit later, maybe next class or class after that. Generalization error is what? Why is it called generalization error? Because the classification machine generalizes. Right? It makes assumptions. Makes assumptions on test data. So a classification machine, you can call it racist. Right? It just looks at some examples and makes some judgments about test data. That is what it does. So when it does that, it will have errors. Even if it is accurate on training data set, it will be wrong on test data. Right? So that's why that error is called generalization error. And what are the components of generalization error, how to minimize it, we'll talk about that. And then we'll talk about overfitting, underfitting. So these are the steps of any classification algorithm. You have training images, you generate image features, you have training labels, you train, you learn model, test image features, prediction. We have already talked about this. What are the different types of features? We are just looking at some examples. So raw pixels is a feature, histograms, GIST descriptor. Anybody knows what is that? Well, we'll talk about that later, but just to give you a brief idea, it's a combination of edge features and frequency of histogram. Oh, not frequency, and frequency of color distribution. Right? It's a combination of these two. So we'll talk about that later, GIST descriptors. So then after the features, you do classification. So what are the different types of classifiers available to us? We can have nearest neighbor classifier. Nearest neighbor classifier is the simplest classifier that we can have. Anybody have heard about KNN? KNN classifier. K nearest neighbor classifier. So this is the one nearest neighbor classifier. The example that I'm showing. It doesn't need any training. You can classify at one go. So what you do? So you have some training examples which are labeled. So training example from class 1 is box. Training example from class 2 is circle. So you have labeled it as box and circle. And then what you have is you have a test data, test example. Remember, you have to have some distance metric, right? So using that distance metric, you see what is the closest data point to this test data, test example. So you saw that this is a box. Box is the closest data point. So you give that this is a box class. And so that is purpose of 1NN. KNN is what? You take the K majority. K majority. If K people say that this is square, you say that this is square. It has to be K nearest ones. Okay? It cannot be further ones. K nearest ones, if they say square, you say it's square. So all we need is distance function, and there's no training required. So that is the simplest classifier we can have. Another classifier is linear classifier. And linear classifiers are very attractive. Do you know why? Why is there so much research and so much so well established documents and code on SVM? SVM is a linear classifier. Right? So why do you have Why do you glorify linear classifiers? Oh, so let's see what is a linear classifier. Very simple. You have this data, you just draw a line. One side of the line is red, one of the other side is blue. So why is this attractive?
Easy to implement, less computational required.
Yes, but what if it's inaccurate? If it's inaccurate, then those don't matter.
We can convert any nonlinear system to a linear system by applying certain functions and then to a linear.
That is not the motivation. What if you cannot? What if you cannot apply kernel to make it linear? Linearly separable.
Easy to train.
Why? SVM is difficult to train, a lot of mathematics involved. Turns out that you can separate any data. Given any data, you can separate it using linear classifiers. What do you have to do? Not kernel transformation, it's different. You have to increase the dimensionality. You have to just increase dimensionality. Let's take an example. Oh. Yeah, let's take an example. So the example is, can you hear? The example is this. Let's say you have this type of data set. These green ones are one class and the red ones are another class. Forget about kernel. Can you separate this using a line? You cannot. Right? Now have another dimension. So here what is the dimension here? 2 dimensions, so you are just plotting x1, x2. Right? You are plotting x1, x2. Where x1, this is one dimension of x1, this is another dimension of x2, right? Now I have another dimension. Instead of plotting x1, x2, you plot this. Oh, you can't. Right, you plot this. So if you plot this, how will it look? It will be a 3D. The green points will be here forming a box, the red points will be here forming a box. You have a plane. Okay? So in this way you increase the dimension. This is not kernel transformation. Kernel transformation does not increase dimension. Right? It does not increase dimension. It will be same 2-dimensional if you do kernel transformation. But this is increasing the dimension. So you increase the dimension and it can be now separated by a plane. So that's why any data point you keep on increasing dimension, you will stop at a point where you can have a hyperplane. That's why linear classifiers are good. But as you increase the dimension, the computational complexity increases. It will take more and more time. So that's why you have other types of classifiers, non-linear classifiers. So you have SVM, so you have so many other classifiers. You don't want to increase dimensionality, but you want to have non-linear class boundaries. Right? So one way is, as he said, kernel transformation. You do kernel transformation, you have nonlinear boundaries. What is the aim of kernel transformation? Same 2 dimensions, but these 2 dimensions are different. are different from are related to the first two dimensions, but they are different. They are so different that in those transform dimension you can have a plane. Right? So there is kernel lesbian, then you have neural networks, you have night base. Night base has very weird shapes, very weird shapes for class boundaries. Bayesian networks, logistic regression, all sorts of things. We'll talk about these. So what we'll talk about is, instead of random forests, we'll talk and RBMs, we'll talk about everything. But very fast. We'll go over them very fast. Now the question is, okay, which one is the best one? For that we need to analyze overfitting, underfitting, test data accuracy. Because we don't worry about training data accuracy. Nobody worries about training data accuracy. If you have high training data accuracy but test accuracy is 50%, not worth it. Then we come to clustering. This is another data mining task. So clustering is what? You give a set of data points. I have no class labels, but the only thing I have is a distance metric. And using that distance metric, I'll say that, okay, some of this data point belongs to class A, some of this data point belongs to class B, and these are all fictitious classes that don't mean anything. So these are clustering. That is clustering. So you have to have some similarity measure. There are many different types of distances. You know, Euclidean distance, Manhattan distance, this, that, a lot of distances. So Euclidean based clustering in 3D space, these are some examples. Many different applications are there in the book. I'm not going to go through all those applications, but one application I can tell you, your grade distribution. Right? That is one curving mechanism that people use, clustering. So what I'll do is I'll take all your attributes, which means all your test scores, all your project scores, those are your attributes, and I'll give it to a k-means clustering algorithm, and they'll give me 4 clusters, A, B, C, D, and you'll get those grades. Now the clustering algorithm doesn't tell me whether this is A, B, C, D, I decide. Right? So these clusters are totally meaningless for the k-means algorithm, but I give meaning to them. Then we have another important data mining functionality, association rule discovery. This is very interesting, and it's used in recommendation systems and also used in big grocery stores, designing different grocery stores. So what is this association rule mining? You have a database. First of all, you have to have a database. Right? So you have a database of transactions. Transactions means you go to a grocery store, you buy something. How many things are you buying and which things are you buying together? So these are transactions that somebody bought bread, Coke and milk, beer and bread, beer, Coke, diaper, milk, and all sorts of things. From this data set, can you extract rules such as, okay, if a person buys bread and milk, there is highly likely that that person will buy diapers. Can you come to those conclusions? Now remember, you have to keep in mind that these conclusions do not have any practical implications. Right? It doesn't mean that diapers are somehow associated with bread and milk. Right? No, it is just the nature of the data. And using that nature of the data, you can take some business decisions. So business decisions may not be practical. It may not have any practical implications, but it gives you money. And you see that it has happened too many times that people buying bread and milk, they buy diapers. It has happened too many times. I don't know whether this is due to the fact that people who drink milk and eat bread need to wear diapers. No, I don't know. Or maybe have babies. That doesn't imply that. Or maybe it might also imply that maybe in that region there are a lot of people with babies. That can also happen. So what reason, we don't know. But there is this rule we came up with, and it happens too many times to ignore. Right? So what you will have, what is the design policy that it will affect? What you do is, in your grocery store, you have bread, you have milk, and right by the side of it you have diapers. Right? So whenever you buy bread, you milk, you see that there is a good diaper deal, you get it. Right? So that is how it involves or it influences policies, association rule binding. So the rules that you mind has no meaning, except that they have occurred too many times. And you can associate some business decisions with it. So here are some examples that people who buy milk, they buy Coke. Why? Because if you see the first transaction you had Coke milk, third transaction Coke milk, fifth transaction Coke milk. So 3 out of 5 times it has happened. So 60%, too many times. Right? So that is the rule that you can discover. You can also discover complex rules. So diaper, milk, goes beer. Right? Those things. So that is whatever we just discussed is in this slide. That you can have consequences, you can have antecedents, and you can also have a combination. Right? So consequences. So potato chips as consequent can be used to determine what should be done to boost its sales. Right? So you are saying that in a grocery store, potato chips are not selling. And then you go to a transaction and you see that, okay, people who are buying bagels are buying potato chips. You have too many potato chips in your store. You have not that many bagels. So maybe you increase the number of bagels that you have, or varieties of bagels. So people who buy bagels, now more people will buy bagels. So if more people buy bagels, then there is more probability that this rule will apply. That people who bought bagels will also buy potato chips. So my sales of potato chips is likely to increase. Okay. So I don't have newer potato chips, but what I do is I have newer varieties of bagels, and it somehow influences potato chips. Why? I don't know. The data says that. Right? Or you can have bagels in the antecedent, which means it can be used to see which products would be affected if the store discontinues selling bagels. And say bagels are not profitable. Somebody told you that bagels are not profitable. It takes too much to bring bagels from far off. Right? So I want to discontinue sales of bagels. But you should be careful, because people who are buying bagels, they are buying potato chips. So which means if you don't have bagels, your potato chips sales will go down. Right? So those kind of rules you can do. And then you can have combinations. So bagels in antecedent, potato chips in consequent. So it can be used to see what products should be sold with bagels to promote sale of potato chips. Right? So you are saying that okay, bagels, potato chips, but in addition to bagels, there are some other things. Coke. People are buying Coke along with bagels. So you know that from practical experience that Coke with chips tastes good. Right? So maybe you see that bagels, potato chips, let's have Coke also. Let's have different varieties of Coke, cherry Coke. Right? It's very bad to drink, but still you have it. Because why? Because some people will buy it and they will also buy potato chips. So those are the decisions that get influenced when you do association rule binding. Right? So one thing that you should remember, that there are no relation to practical, there are no practical implications of the rules. It's just how the data is. And there might be practical implications, but it might not be the correct one that you are thinking. There may be too many practical implications, and you don't know which one is at work. Right? So that is what they are saying, association. And then there is regression, predicting using linear predictors. So, wind speed or energy harvesting. People do energy harvesting, right? Wind harvesting, solar harvesting. Turns out that you can determine solar irradiance. Solar irradiance means if there is no cloud cover. If there is no cloud cover, then you can build regression models of solar irradiance, which means that you can predict in the future how much irradiance you get from the solar cells. Okay? So these are called ARIMA models, ARINA, ARIMA models. These are linear regression models. So which means that it represents the future value as a linear combination of the past values. So if xt is the future value, then xt is equal to a1 xt minus 1 plus b1 xt minus 3 plus c1 xt minus 13, something like that. a1, b1, c1 are coefficients. So that is regression. That is also predictive. And then you have anomaly detection. You take data, and there might be some problems with the data. Anomaly detection is very important these days. I assume you know anomaly detection. Credit card bills, you have a specific pattern of buying stuff. Suddenly you buy something worth $2,000, your credit card company calls you. Why? Because you deviated from the pattern. You never buy $2,000 worth of stuff. So you deviated from the pattern, and there is some algorithm that detected the deviation. So that is data mining. Now, what knowledge you extract from it depends upon the credit card company. That is not task of data mining. Data mining just gives you deviation. It says, okay, I saw your records, and these are the points where you deviated. So patterns, it finds out patterns, and using those patterns, the bank derives the knowledge that, okay, maybe your credit card is stolen. So that is the anomaly detection. Anomaly detection has a very important application, which we'll discuss a little bit later. Yeah, let's not get into that. We'll take time. So what are the challenges of data mining? There are several challenges. First of all, scalability. What is scalability? Now, when you talk about scalability, when anybody talks about scalability, it's a very tricky term. Scalability is a very tricky term. Scalability as such doesn't mean anything if you don't specify the measures. So scalability has an implication that something is increasing, and as an effect, there are some constraints that are getting pushed. So whenever you talk about scalability, you have to tell me what is increasing and what are the constraints. Right? So in this case, what they mean by scalability in data mining is that the dimensionality is increasing. Dimensionality is increasing means we are getting data from more and more sensors. The dimensionality is increasing, and we cannot analyze the data as fast. So it's pushing our time constraint. Scalability is a very important aspect for data mining. It's pushing our time constraint. Too much data. We have to have new algorithms. Traditional algorithms are first very time consuming, second suffer from curse of dimensionality. They are losing their accuracy. There's too much data, too much unnecessary data to delete. So scalability, dimensionality, complex and heterogeneous data. Everybody knows about IoT, Internet of Things, I'm assuming. So Internet of Things means that there are sensors, you deploy sensors on anything. Maybe this table, maybe this microphone. Oh, it already has a sensor. Maybe that table. Right? So you put the sensors on that and you just collect data. What data? I don't know. Just collect data and see what happens. You can have a lot of good applications out of it. But the problem is, these sensors are commercially made. These sensors are application specific, commercially made. So if they are application specific, then they do not follow general protocols, general standards. So you have heterogeneous data coming at different sampling frequencies, different formats, and with different definitions. How do you mine all these heterogeneous source of data? You have to have one mining algorithm. You cannot have tens, thousands of mining algorithms. That's a big challenge for data mining. Data ownership and distribution is a concept that is related to security. This is one very interesting concept. It's also called provenance. Provenance, data provenance. So data ownership and distribution. Let's take this example that I discussed this example in the mobile computing class. So if anybody is there in the mobile computing class and taking this class, it will be boring. So take this example that you have, a person has diabetes, or not diabetes, let's say the person is overweight. And the person is overweight and he goes to a doctor. So the doctor says that, okay, you need to run. Right? You go peak Arizona heat 4 p.m. during summers, run for half an hour. You do this 15 days, you lose 20 pounds. And it says that. And so the doctor says that, okay, I am keeping an eye on you. I am giving you this accelerometer sensor. You wear it, the data will directly come to me. I won't give you the data. And I will monitor when and where you are running. And so I will have accelerometer, I will have GPS. So take this wristband, Fitbit, run. So the person comes home and the person doesn't feel like running, especially at 4 p.m. So what he does, he or she does, is that tells the son or daughter that you take my Fitbit and you run. Right? The doctor doesn't know, data is coming. The doctor doesn't know from whom the data is coming. So this person puts the entire burden on the daughter or son. The son or daughter gets skinny, but this person remains fat. So now this person goes back to the doctor and says, oh, I did so much running, it nothing reduced, give me some medicine. The doctor is not going to give the medicine. It's against medicine. But the doctor says that, oh yes, he has run so much. So is it the problem that running doesn't work for him? Or doesn't work at all? Right? So that's the total misinformation. Right? So here this is a problem of data ownership. So who owns the data? Is it the person's data or is it the son's data? How do you know? Right? Because it's a problem with the data source itself. The source is denying. So what you can do, this is not data mining as such, but this is kind of knowledge retrieval. So what you could do is you have multi-data fusion, multi-sensor fusion. So what you do is, have you heard about ICM, insertable cardiac monitors? Right? What you do is, there's a very small cardiac monitor, they monitor the heart rate, and you put it inside the rib cage. Very small surgical procedure you do, you put it inside the rib cage. So what the doctor does is the doctor takes an ICM, puts it in the person. Now the person cannot open up the ICM and give it to the child. Right? So person has the ICM, but the person still doesn't feel like running, gives the accelerometer to the child and the child runs. Okay? Now the doctor is getting two information, accelerometer from the child, heart rate from the person. He sees that the person's heart rate is 50 beats per minute, but running at 4 miles an hour. That can never happen. If you run at 4 miles an hour, your heart rate should be 150. So now you know that these data are coming from two different sources. Right? So that's how you solve data ownership problem using data mining. So that is another challenge that data mining should look into. Then data quality. Since there are sensors, there will be errors. There will definitely be errors. And you will see it when you do your assignments. Last time we saw it. A lot of errors. And wrong annotations and all that we saw. So you will face that problem firsthand. Then privacy preservation. In this assignment that you do, there is no privacy because video record and you publish the videos. So you know from whom the data came. But that is not good. So you should always preserve privacy. So you have to do data mining, but in a private way. Now, why is it a problem? How can privacy be violated? Let's say insurance policies. Right? There's an insurance company. An insurance company should take their policies. So they are saying which ones are the pre-existing conditions. So if which ones are pre-existing conditions can be determined by what? Many factors. But one of the factors is which is the costliest. Right? Make it pre-existing so that we don't have to pay. So which one is the costliest, that is one thing. But then in order to do not only costliest, you have to also see which ones are most frequently occurring or least frequently occurring, or what is the frequency of occurrence, right? So if you, now when you make policies in general. You do not make policies for individuals. You cannot say that, okay, you have this condition, so let's make it pre-existing for you, so we don't have to pay. You cannot do that. You can say that pre-existing condition is for the general public, right? Now when you get the data from public, you have to do an anonymous analysis. You have to do an anonymous analysis and then find out the frequencies of pre-existing conditions and then take your decisions. But if that privacy agreement is violated, then what a company can do is it can take the data of that particular person, figure out that that particular person has a bad condition, make that pre-existing for him. You can do that. So that's a big problem. So you have to mine data because you want to understand what are the frequencies of different diseases. But it has to be in a privacy preserving manner. So that is a big challenge. Data mining in a privacy preserving manner. A lot of research is going on. So that is the introduction. That is the first chapter. Let's go to the second chapter. Any questions? If you have any questions, you ask me immediately.
What is streaming data?
Where is streaming? Oh, streaming data. Okay. So streaming data is another problem. So if you do data mining in the cloud, so you are doing data mining in the cloud on sensors. Imagine this is brain sensor. Brain sensor has 512 hertz data, hertz sampling frequency. So you have to have a real-time application on using brain sensors. So what you have to do is you have to stream this brain data to the cloud, and the cloud has to process it online. Now there are a lot of challenges in the sense that this high frequency data, you have to stream it very fast to the cloud. The cloud has to compute it, on it very fast and give the results back very fast because everything has to be low response. So that is the challenge. How do you stream data through the Wi-Fi or 4G network which might have limited bandwidth? Right? How do you stream the data, compute, give back the results while maintaining very low response time? Any other questions? Yes.
What is the regression and dimensional reduction function of continuous?
Why?
In continuous data, you mentioned that regression and dimensionality will be part of
Yes.
continuous. How is that?
So regression, every value is a class in regression. So if every value is a class, a parameter can take infinite number of values. Uncountably infinite number of values. It is real numbers. Regression works on real numbers. Okay? So that's why it is continuous. Dimensionality reduction is same thing. It works on real numbers. It works on real numbers to reduce the dimension. So infinite number of classes. Any other questions? Okay, let's go to chapter 2, which is about data. So some of the concepts we have already talked about. So what is data? Yes, there are some data objects and attributes. So objects are the rows. Each row is an object and each column is an attribute. And the values that we have for an object, those are attribute values. So if we take a matrix or an array, then a column, or no, a row has some values and you can call it attribute vector. Right? So these are all attribute values. You can also call it feature vector. And you can also call one column as a feature. So feature vector, attribute values, you have to make these distinctions. Right? And a collection of objects is data. So you have to distinguish between attributes and attribute values. Attributes are dimensions and attribute values are real numbers, actual numbers or strings. Right? So there can be many different types. So these are the different types of attributes. It can be nominal, which means strings. Examples include ID numbers, eye color, zip code, whatever you can express using some string. Right? So nominal attributes or ordinal attributes. Ordinal attributes means there is a specific order in the attributes. Example is ranking, right? Ranking in the class is an example, ranking in sports is another example. So these are ordinal attributes. Then you have interval attributes. Interval attributes means it's associated with a range of values, right? So interval attributes example include calendar dates, temperatures, Celsius, Fahrenheit, those things. Or you can have ratios. So ratios means it's division. For example, length, meters, centimeters. So whatever you have, you divide by 1 meter and you get that result. And so that's why it's a ratio. So there are various properties. There are various properties of these different types of attributes. Right? So the properties, there are 4 classes of properties: distinctness, order, addition, and multiplication. These are the different properties of attributes. So what is distinctness? Distinctness means whether it's equal or not equal. That is distinctness. Equal to or not equal. Then what is order? Order means you have to have some greater than, less than functionality. Addition means addition, subtraction, and multiplication means multiplication, division. So these properties, some of the attributes will have these properties and some others will not. Right? So nominal attributes, they don't have the order, addition, multiplication properties. They can have distinction properties. So you can say that this is the same name, right? It's the same ID number. Or you can say these are 2 different ID numbers, 2 different names. But you cannot say, okay, one name is greater than the other. Right? You cannot say that. Maybe you can order. You can make them ordinal if you order with respect to in an alphabetical order. And if you do alphabetical order, then you can have an ordinal attribute. Right? So ordinal attribute means it has distinctness as well as order. So rankings or names arranged in an alphabetical order, those are ordinal attributes. Interval attributes have distinctness, orders, and addition. So you can add and subtract. Ratio has all the 4 properties. So you can have distinctness, order, addition, multiplication, everything. Right? So then the book goes in very much details about some examples and why these descriptions are important, what are the different types of operations you can perform on them. We won't go in details about these. It's not that important. Transformations. Let's talk about transformations. These are important. So you can do transformations on attributes. This will need a little bit later we'll need this. So what kind of transformations can you do? What is transformation first of all? Transformations means transformation means you apply certain operation on an attribute and the result is the same attribute. You cannot do an operation on one attribute and you make it some other attribute. You cannot do that. For example, having the nominal attribute and ordering it in an alphabetical order is not a transformation, because that makes it an ordinal attribute, so it changes the attribute. So nominal attribute, so what kind of transformation you can do? You can have permutations. Permutations are fine. Don't sort. You can have permutations. So A, B, C, D, C, D, E, F. Right? That is a transformation. So transformation occurs on the same attribute value. You cannot combine 2 attribute values in transformations. Whenever a transformation is a function that takes 1 attribute value as input, it cannot take 2 attribute values as input. So if you have nominal, it's a permutation of value, just 1 attribute. Ordinal, you can have some monotonic function. What is monotonic function? Increasing function. Right? So for example, you can replace 1, 2, 3 by 0.5, 1, 10, still maintains the order. Right? So it has to be a monotonic function. On an ordinal attribute, you can do only those kind of transformations that preserve the order. If it doesn't preserve the order, then it's not a transformation, not a valid transformation. Then interval, what you can do? Interval, you can just do linear operators. A multiplied by the interval plus B. You can do that kind of transformation. And ratio, what can you do? You can just multiply or divide. A can be a fraction. So these kind of transformations are allowed, because if you do these transformations, it won't change the attribute value. So we have to stop here. Okay. Next we'll discuss discrete continuous and we'll finish this task.